Hello and welcome to Math with Mrs. Becker. Today in college algebra, we are starting a mini chapter that really focuses on rational function. A rational function is the quotient of two polynomials. Remember, quotient means that you're dividing. So in a sense, when we are talking about a rational function, it means we have one polynomial over another polynomial, creating a fraction. In general, when we talk about the domain of a rational function, it's going to include all real numbers except any x value that would make the denominator equal to 0. Because remember, in math, we can never divide by 0. Now, a lot of what we're looking at today, we want to see what happens graphically as you approach these values that would make the bottom a 0. Okay, so really we're studying something that are called asymptotes. Let's go ahead and look at this. So my first example, the function is 1 over x. Part A, they want us to find the domain. Remember, your domain is all real numbers except for anything that would make the bottom a 0. Well, the bottom is just an x. So your domain is x cannot equal 0. You cannot put a 0 here. It can be anything else though. Now what we really want to study is, okay, well, x can't be a 0, but what happens as you get close to the 0? So we really want to look at as you're coming from the left, getting closer to x equals 0, and as you're coming to the right, what's happening graphically? So one of the easiest ways to do that is to go ahead and make an xy table. If I go ahead and I have 1 divided by, and I'm just going to put my parentheses, well, obviously if I put in a -1, we know this is -1. If I up arrow and change this to -0.5, this is -2. If I go ahead and change this to -0.1, ooh, that's a -10. If I go ahead and I insert a 0 here, so it's -0.01, that's -100. If I go ahead and I insert another 0, so it's -0.001, this is -1000. So what's happening, we are coming in at 0. We know that you cannot have 0. So this is like a lava line. You cannot have x equals 0. So what we want to know is as we're coming this way, notice that the values keep getting smaller and smaller and smaller and smaller. So the graph is going to be going like this. As it gets closer and closer to 0, the y value drops significantly. So the way that you show that, as x approaches, this time we're approaching 0. We're not approaching infinity. We're approaching a 0 from the left, from the negative direction. Our function is approaching, it keeps getting smaller and smaller and smaller and smaller, so negative infinity, meaning as you come to the left, you're going to have an arrow going downwards. Now let's see what happens as we come from the right, because I'm starting at 1, I'm going to go 0.5. 0.1, 0.01, and see as we get closer what happens. So 1 divided by, well, okay, we know 1 divided by 1, we've got a 1. If I go ahead and I change it to 0.5, not the tangent, there we go, that's a 2. Now I'm going to change it to 0.1. We're getting closer and closer to 0 from the right. This is a 10. If I insert a 0, it would be dividing by 0.01. That's 100. Look at that jump, 2 to 10 to 100. What do you think is going to happen next? If you said it's going to go up, you are a genius. So that's up to 1,000. So as I'm coming from the right, every single time that we got put in a value that was closer and closer, it was a higher y value. So what happens is we can see that as x is approaching 0, it's approaching it. It doesn't equal 0. We're getting closer and closer from the right. That's what that plus sign means. Our function, the y values were getting bigger and bigger and bigger, so we were having an arrow going upwards. Okay, now D, what they want us to do is go on a graphing calculator. I'm just going to jump onto Desmos here. 1 divided by x. They wanted us to see this. So notice as we were coming from the right, our y values are getting closer, or getting larger and larger and larger as we got closer to x equals 0. As we were coming in from the left, our y values were getting smaller and smaller and smaller as you got closer to 0. One other thing to notice, so this is called a vertical asymptote because your asymptote is a vertical line. This graph also has what's called a horizontal asymptote, and that's another thing that we are looking at today. As I go all the way to the right, it's getting closer to 0, but if I zoom in, notice it doesn't touch it. It just keeps getting closer. So as I go all the way to the right, then let's go back here. I'll just hit home. There we go. If I go all the way to the left, same thing. If I zoom in, yes, from far away, it looks like it's touching, but it's not. So this graph also has a horizontal asymptote where y equals 0. And we'll talk about y in a little bit. Okay, let's look at another one. This is a rational function. We want to first, part A, they want to know what the domain is. Remember, your domain is any real number except for something that would make the bottom a 0. The only thing that would make the bottom a 0 is a positive 1. So x can be anything except for 1. So what's happening is if I go ahead and I graph, here is 1. Okay, so I'm going to have an asymptote here. This is x equals 1. If I start at 0.5, then go 0.9, 0.99, this is coming in from the left side. Now here, if this is 1 and I'm coming in at 1.5, 1.1, 1.01, this is coming in to the right. So that's how they got these values. They want to get close to x equals 1, although we can't make it equals. That's why it's just getting really close. And you want to make sure you're coming in from the left and the right. Now this one's going to be a little bit harder. On the top, I'm going to go ahead and put parentheses 5 times whatever the value is. I'm starting with 0.5. Close it. So there's the numerator. Divide by the bottom, same thing, 0.5 minus 1. I got negative 5. Now if I change my 0.5s to 0.9s, go up, arrow, 0.5, change that to 0.9, there should be 2 spots, 0.9, ooh, negative 45. If I change them to 0.99, I just need to insert an additional 9, I'm getting closer and closer to 1, insert an additional 9, so it's 0.99, wow, negative 495. Now if I make it 0.999, insert an additional 9, go to the other place where I had an x value, insert an additional 9, so now it's 0.999. We have negative 4,995. So as we were coming in from the left, because we started right here, as we got closer, it was negative 5, negative 45, negative 495, negative 4,400, or negative 4,995. So what we see is as x approaches 1, we're approaching 1 coming from the left. Our function, the y values were getting smaller and smaller and smaller, so we would have an arrow going downwards. Okay, now let's see what happens as we're coming from the right. So again, I have 5 times, we're starting with 1.5, that's the top, divided by whatever x is. We're starting with 1.5 minus 1. This is 15. Now I need to change my 1.5 to 1.1. It's getting closer to 1 coming in from the right. Those of you who are planning on taking calculus at some point, we do something very similar when we talk about limits. Let's go ahead and go 1.01. So it's kind of cool because I will refer back to this lesson when you're in calculus next year. Hopefully you choose to take that class. It's super fun. Go ahead and insert another 0. So what I notice is as I'm coming in from the right side, because I started at 1.5, then I got closer, so it was 15, then it was 55, then 505. So notice that as we got closer coming from the right, the values were getting larger. Oh, sorry, there we go, there's the picture. So as we were coming in from the right, the values were getting larger. So as x approached 1 from the right, our function, the y values, were getting larger. Now remember on the last one I pointed out what's called a horizontal asymptote? In order to see if something has a horizontal asymptote, they occur as you go all the way to the right or all the way to the left of the graph. So what you want to do is go ahead and pick x values that indicate you're going way, way to the right. So here we're going all the way to the right of the graph. If I put in a 5, we want to see what happens. So 5 times 5, there's the numerator, divided by 5 minus 1. Okay, I got 6.25. Now if I go ahead and I change this to a 10. Just a lot of calculator stuff here, guys. Oh, whoa, when I put this in as a 10, It's 5.5 repeating. Now if I go ahead and I change this to 100, this would be 100 minus 1, perfect. This is 5.05. If I change this to 1,000, perfect, it's 5.005. So one thing that I noticed is as we went to the right, and I'm talking bigger values, 5, 10, jump to 100, jump to 1,000, notice it kept approaching what value? If you said 5, I'm giving you a virtual high five because you're a rock star. As x approaches positive infinity, this is our end behavior. Your function was approaching 5. Your end behavior does not always have to be an arrow going up or an arrow going down. If you have a horizontal asymptote, it's going to approach a number. Super cool. Let's see what happens as we go to the left. So here, we're going to the left. I'm starting -5, then jump back -10, -100, -1,000. So let's go ahead and see what happens. So it's 5 times, we're starting with -5, taking that value, divided by -5 minus 1. I have 4.16 repeating. Now if I change it to -10, go ahead and change the 5 to a 1, insert a 0. I have 4.5454. It repeats. Now if I have -100, I just need to insert a 0. Lots of calculator stuff, guys. Insert a 0. Ooh, 4.95. What do you think is going to happen now? Let's put in that extra 0, making it 1,000. Make a guess, be a scientist. Whoa! 4.995. So as I continued to go to the left, and I'm talking big strides, -5, -10, -100, -1,000, your y values were getting closer and closer to what? If you said 5, you're a rock star. As x was approaching negative infinity, as I'm going all the way to the left, my function was approaching the y value 5. So now what we want to do is go ahead and graph this. Desmos.com is amazing because we can get a visual of this. Let's go ahead and go to Desmos. And if I graph this, one thing you want to do is put the numerator in parentheses because you do have more than one value that's on the top of the fraction. So 5x goes over x minus 1. Okay, if I go ahead, wow, look at this. Okay, so we said that we should have an asymptote at 1. So if I zoom in here, 1, 2, 3, 4, 5. So here is my asymptote. It said as we're coming in from the right, we should have an arrow going upwards. Notice as we get to the right, it sure does that. As we come in from the left, as you're getting closer to 1, your values are getting smaller, so there's going down to negative infinity. We said we had what's called a horizontal asymptote. As I'm going all the way to the right, it's getting closer and closer to 5. Here's that 5 line. It's getting closer and closer and closer, but look at that, it doesn't touch. As I go to the left, same thing. My asymptote was a 5. Like here, it looks like it's touching. Zoom in though. That's not touching. It gets really, really close, but it will never actually touch it. It's such a cool thing. So here we have what are called vertical asymptotes and horizontal asymptotes. Awesome, turn the page. In the previous example, if we looked at example 1, we had 1 over x. We talked about our notation. So as x was approaching 0, this means from the left, our y values were getting smaller, so you would indicate that by showing that your function is approaching a negative infinity. As we were approaching 0 from the right side, our function, the y values were getting bigger, okay? And it was always close. We were looking at what happened near 0 because 0 is the value you could not put on the bottom of a fraction. In this case, x equals 0 was a vertical asymptote, but this graph also had a horizontal asymptote. Remember when we graphed it, it was getting closer and closer to the x-axis, but it actually wouldn't touch it. So you had a horizontal asymptote. It is a horizontal line. So remember when you have the equation of a horizontal line, it is cutting the y-axis, so it's always y equals whatever that value is. And what that means is exactly what we were writing out in our previous example. As we go all the way to the right, your graph is approaching, it was approaching 0. As we went all the way to the left, our graph was approaching 0. Again, vertical asymptotes, because they are up and down, they cut the x-axis, so it'll always be x equals whatever that number is. Horizontal asymptotes, because you are cutting the y-axis, it will always be y equals and whatever that value that it's approaching. Here are some examples. This is a that's a vertical asymptote. When you have vertical asymptotes, you'll notice that your graphs are always going to either be approaching positive infinity or negative infinity. If you have a horizontal asymptote, it's going to be approaching some number. Here again, vertical, approaching positive or negative infinity. Vertical, approaching positive or negative infinity. This one is horizontal. It's okay that this middle piece did cross, because a horizontal asymptote means as you go all the way to the right and all the way to the left. If I go all the way to the right and the left, my graph is approaching but not touching zero. Okay. How do you find horizontal and vertical asymptotes? Well, there are some rules, okay? Number one, if you're looking for vertical asymptotes, they will be located at the zeros of the denominator. It's wherever you would have a zero on the bottom of a fraction, so it's your domain limitations. That's where you'd have a vertical asymptote. Horizontal asymptotes, there are 3 rules, and they talk about the degree of the numerator and the denominator, okay? So what happens, remember your degree is the largest exponent on your variable. If your if your numerator has a lower degree than the bottom. So something like this. Let's say I have x plus 2 over x squared plus 1. The degree here is a 1. The degree here is a 2. If the top degree is less than the bottom, you have a horizontal asymptote at y equals 0. If your degrees are equal, let's say this is x squared and this is x squared, you take the leading coefficients. So in this case, it would be 1 over 1. That's where your horizontal asymptote would be. You divide the leading coefficients. If the top is bigger, if this is a 3, if the top degree is larger than the bottom, you have no horizontal asymptotes. So again, if the top is smaller than the bottom, y equals 0. If the degrees are the same, you divide the leading coefficients. That's going to be your horizontal asymptote. If the top degree is larger, like here, top degree is 3, bottom is 2, then you have no horizontal asymptotes. So let's take that information and let's try to find some horizontal and vertical asymptotes. So vertical asymptotes occur where the bottom would equal 0. So I can go ahead, take the bottom, set it equal to 0. So 3x squared equals, if I minus 1, go ahead and divide by 3. So x squared equals negative 1/3. If I take the square root of each side, notice it's imaginary. That means that there are no vertical asymptotes. Because when I tried to find my vertical asymptotes using the method that they told us, take the bottom, set it equal to 0, when I went to solve it, I had something imaginary. That means there are no real vertical asymptotes. Now I look at the degree. The top degree is 1. The bottom degree is 2. If the top is less than the bottom, like we have here, you have a horizontal asymptote at y equals 0. So this means as you go all the way to the left and all the way to the right, your graph will approach but not touch 0. Let's go ahead and graph it. I just really think a visual is a good thing as we're learning this. So there we go. Get rid of that. I have the group 2x. We're going to divide that by 3x squared plus 1. Notice there are, just like we found, there are no vertical asymptotes. Nowhere in the middle of the graph are that thing shooting up to positive or negative infinity. It's kind of a fun looking graph, but as we go all the way to the right, notice it's getting closer and closer to 0. As I go all the way to the left, same thing. If I zoom in, it's not touching that line. It may appear to be, but as you zoom in, it is not. So we do have a horizontal asymptote. Our graph is approaching the same value going to the left and the right, but we don't have any vertical asymptotes where it needs to shoot up or down to positive and negative infinity. Okay, let's look at the next one. If I want to find vertical asymptotes, x squared minus 1 equals 0, I can factor this. I can do the difference of squares, making this x plus 1, x minus 1. To find my vertical asymptotes, set each piece separately equal to 0. So if I minus 1, 0 minus 1 is a negative 1. Here, if I add 1, 0 plus 1 is 1. So I have vertical asymptotes at x equals 1 and x equals negative 1. So graphically, that means I'm going to have an asymptote, so it's going to be shooting up to positive and negative infinities at those two locations. Now, if I look for horizontal asymptotes, you compare the degree. The degree of the top is a 2. The degree of the bottom is a 2. If your degrees are the same, you divide the leading coefficients. So my horizontal asymptote, the leading coefficient on the top is 2, divided by the leading coefficient on the bottom is 1. So my horizontal asymptote is y equals, because it's a horizontal line, so it cuts the y-axis, 2 over 1 is a 2. So let's go ahead and graph. Peanut butter saying hi, guys. Okay, so if I go ahead and I graph this, I'll graph this, and then if she's still barking, I'll go to a part 2. So if I have 2x squared and I divide it by x squared minus 1, notice I should have asymptotes a negative 1, positive 1, so those are vertical. Then horizontal, we said that it should get close to as you're going all the way to the left and the right. Doesn't matter what's happening in the middle. As I go all the way to the left and the right, it should be approaching 2. And that is what I'm seeing. So here it looks like it's at 2, but it's not. Notice it's a little bit higher. So as I go all the way to the right and I go all the way to the left, you'll notice that it's getting closer and closer to 2, but it doesn't actually touch it when you zoom in. So this was a good way to check. Negative 1, positive 1, we have those vertical asymptotes where it shoots up to positive and negative infinity. All the way to the left, all the way to the right, we have our horizontal asymptote. Okay, one more thing that we want to talk about today is if you have a hole in the graph. Now here's the cool thing. You can actually have a graph that looks like it's continuous, like it goes forever and ever and there's no issues. But when you zoom in, there's actually a hole. And that hole is one little value where if you filled in the next value into the original function, that you would end up with a domain error because it would make the bottom a 0. So in the next examples, we look for horizontal and vertical asymptotes, like we just did, and to see if there's any holes that would appear. Okay, what you have to do is step 1, okay? Step 1, see if you can factor these. Okay, the way that you can find the holes is to go ahead and factor. On the top, I can factor this to x plus 2, x minus 1. On the bottom, I can factor this to x minus 3, x plus 2. Now what happens? If you can factor the top and bottom and you can cancel, if I go ahead and I can cancel a group, wherever that x value is, that's where the hole is located. I can cancel this. So what I have left is x minus 1 over x minus 3. But I still cannot have an x equals a negative 2 because it would make the bottom a 0. So I have a hole at x equals negative 2. And the reason why it's negative 2 is because to find the x value to solve, I would have x plus 2 equals 0. You would have to minus 2. So there's going to be a hole in the graph. Your vertical asymptote, once it's simplified, it's x equals whatever make the bottom a 0. So I'd have a vertical asymptote at x equals 3. Your horizontal asymptote, go back and look at the original. Both of these polynomials have a degree of 2. So in order to find your horizontal asymptote, you divide the leading coefficients. The leading coefficient here is a 1. The leading coefficient here is a 1. 1 over 1 is 1, so we have a horizontal asymptote at y equals 1. So let's go ahead and graph this. I'm going to show you. It looks really cool. I have my phone on Do Not Disturb so nobody bugs us. Then the dog starts barking. Sorry about that. The joys of making videos from at home. All right, so when I go ahead and do this, you want to have parentheses. So it's x squared plus x minus 2. Now, Desmos knows, okay, that's the top. Divide. Now whatever I put in is going to be my denominator. X squared minus x minus 6. Now we want to check out what's going on. Okay, I said that I should have a vertical asymptote at 3. So at x equals 3, that's when you'll notice things are shooting up to positive infinity, things are shooting down to negative infinity, right? And we should have a horizontal asymptote at 1. So as I go all the way to the right, and as I go all the way to the left, you'll see that it's approaching that 1, but it will not break the barrier. But you're probably like, well, Mrs. Becker, what the heck? You told me that there's a hole at -2, and I can't see the hole there. Well, check this out. Go ahead and trace. Come on, buddy. When you trace, I hope you can see this. If I get, oh, did you see it? Did you see it? Did you see it? -2 is undefined. You can't tell looking at it, but when you go ahead and trace along there, as soon as you get exactly on -2, there's a hole there. You cannot have -2 because if you put that value into the original, you do end up with a 0 on the bottom. So that's what happens when you have a hole in the graph. You can't see it. So you find it and you go ahead and you trace, and when you get to that value, there we go. When I get to the value, we were there. It is undefined. It is actually a hole in the graph. You just can't see it. Super cool. Okay, let's look at a couple more. If I want to find horizontal, vertical asymptotes and holes, step 1, see if you can factor. 2 numbers that multiply to 1 and add to 2. Well, I have x plus 1 and x plus 1. Bottom, I can factor it. It's multiply-add method because there are 3 terms. The first value has to be multiplied to the last value because I do have a number in front of my squared term. 2 times -3 is -6. I'm adding to a -1, so it's -3, positive 2. Because there's a number in the front, these 2 values replace the middle. The first term stayed and the last term stayed. The middle term that's being replaced has an x. So when I put in my -3 and my positive 2, I have to make sure that I also give them an x. Group it. These 2 terms share an x, so I can take that x out. This group already matches this group. If they match, you take out a positive 1 because what I'm doing is I'm dividing this group by 1. If I divide by 1, it's not going to change it. Whatever you were able to take out, that forms a group. So x plus 1. What they have in common, that's a group. So there's step 1, factor the top, factor the bottom. Now, if you can simplify something, I can. If you can cross off something on the bottom, that's where you're getting a hole in your graph. We have a hole at x equals -1. So when I go ahead and graph this, if I trace, when I get to -1, it's going to say undefined. If you look at the graph, though, you're not going to be able to tell just by looking at it. So it's important that you understand how this all works. Now when I'm trying to find my vertical asymptote, whatever's left on the bottom, 2x minus 3, whatever would make that piece a 0, that's your asymptote. So if I add 3 and divide by 2, x would be 3/2. So if I go to the right 1.5 units, that's where I'll have a vertical asymptote. A horizontal asymptote, you look at the degree. This has a degree of 2, this has a degree of 2. If the degrees match, it's y equals, you divide the leading coefficient. Top leading coefficient is 1, over bottom leading coefficient is 2. So I have a hole at -1, a vertical asymptote at 3/2, and a horizontal asymptote at 1/2. Okay, let's go ahead and graph this one. See what this looks like. On the top, I have x squared plus 2x plus 1 over 2x squared minus x minus 3. Now we want to check all of our work here. So I should have a vertical asymptote at 1.5. So there should be a spot a little bit over 1 where your graph either goes up to positive infinity or down to negative infinity. Yes. If I look left and right, you can tell that there's a horizontal asymptote. Okay, it's going to get closer and closer to a value. In this case, our value is 1/2. Now we have to make sure that there is a hole at -1. See, if I zoom in, you guys look at that. You can't even tell. You can't tell at all. But when I go ahead and I trace, -1 was really fast there. Did you see it? -1 is undefined. There is a hole there. Okay, so that's how you can check this graphically. The rest of the video, I'm just going to go ahead and go through the process. You guys are comfortable with Desmos. You know how to do that. So I will just I wanted to make sure you could see how you could check our solutions. Number 3, Houston, we have a problem. These polynomials are not in the right order, so I'm going to go ahead and rewrite them in standard form. So the top is negative 5x squared minus 14x plus 3. The bottom is 2x squared plus 7x plus 3. Okay, so that's what I actually have here. Factor on the top multiplies to negative 15, adds to negative 14. Well, that's negative 15 and 1. So the first term stays, the last term stays, the middle term changes into negative 15x and 1x. Go ahead and group it. I can divide out a negative 5x. That would leave me with x plus 3. This is already x plus 3, so I go ahead and take out a 1. So factored, it's negative 5x plus 1 and x plus 3. Okay, the bottom. Multiply, add method as well because there are 3 terms. 2 times 3 is 6, add to 7. Well, that's a 6 and a 1 because 6 times 1 is 6. 6 plus 1 is 7. The first term stays, the last term stays. The middle term is replacing the term that contained an x. So when I put in my positive 6 and my positive 1, I had to make sure that they both had an x. The first group, I can take out 2x. That would leave me with x plus 3. This is already x plus 3, so I take out a 1. That way I do not change anything. When I write it in factored form, 2x plus 1 is a group because that's what I took out. X plus 3 is a group because that's what they have in common. Now here, if I can cross something off on top and bottom, like I can, whatever you cross off on the bottom, that creates a hole. So we have a hole at x equals negative 3. Now whatever's remaining, that's how you find your vertical asymptote. 2x plus 1, set that equal to 0. If I solve for x, I minus 1, divide by 2, so x equals negative 1/2. That's a vertical asymptote. Your horizontal asymptote, you go back to the beginning. I'll look at where I went ahead and put it in standard form. This has a degree of 2, this has a degree of 2. So I do have a horizontal asymptote. It's where you take the top leading coefficient divided by the bottom. So y equals negative 5/2. We found the hole, the vertical asymptote,